My screen is visible.
Yes, sir. Yeah, it is visible now.
Okay. So where you listen this term amortize actually,
Week
then I
4,
can find B
uh,
core. Okay.
BFS 4.3, timestamp 20 minute 40 second.
Okay. Good. So that terms is used in the slides or search
No, no,
you.
no. You played the video, no? First you played the video.
Mhm.
20 minute 40 second.
20 minutes, 40
20 40. Yeah, 20 minute.
seconds.
Yes, yes, this one. An example of amortized analysis. How this is adjacency list, BFS with adjacency list is actually
Okay,
this
okay,
part is not
uh,
clear. Yeah.
okay. So BFS with adjacency matrix and step two initialize each vertex. Okay, and step two explore each vertex. Overall time is order of n square. BFS with adjacency matrix. Okay, so n step to initialize each vertex. 2m steps sum of degree to explore all vertex. An example of amortized analysis. Overall time is n plus n. Okay, so BFS with adjacency matrix. So this is fine. 2m step sum of degree to explore all vertices. So so here m is what is m? So n step to initialize each vertex. So n is the number of vertex, and
Mm-hmm.
m is basically a number of edge. Okay, so 2m sum of degree to explore all vertices. Okay, 2m. So here adjacency matrix, number of edge. You have to see the algorithm as well. Okay, so just wait here. B4. So that was search BFS, and this is I think adjacency matrix. Uh, list. Yeah, so this is the algorithm. So while not recent it in this okay, so the restriction an example of analysis. Okay, so in that terms, I have to see the whole topic again. But otherwise, amortize means I'm just explaining in the these things. So in the hashing terms, okay, we use this term in to represent the complexity type of things. Okay, so for example, if we have a hash table, okay, so we have a
Okay.
okay, we have a 10 place empty. So this is
Mm-hmm.
just an example. So for example, 0, 1, 2, 3, 4, 5, 6, 7, 8, and 9. Okay, and every time we are using one hash function, we are generating this index using a value. So for example, if we have a k mod, uh, for example 10, okay, yeah, if k is our value, okay. So what we said that what is the complexity of searching in hashing? So that what is the complexity of
in
searching in hashing?
in
Searching in hashing.
searching in login.
No. So for example, if you want to insert a element, here k is the data. So if you want to insert k33 into this hash
Okay,
table, okay. So using this function, we generate the address. So 33 mod
mod 10
10, this
3.
return 3. Okay, so we will directly store this 33 at this place. Okay, using this function, we can directly store this 33 into this is 3 index. So this is
Mm-hmm.
big O one operation. Okay, same things we can use in the searching operation. So at the searching time, if we are finding out that what where is the 33, okay, so we
Mm-hmm.
can directly apply this hash function, and uh, this hash function, so using this hash function, this hash function will return the same value 3 for this data 33, and we can directly access this 3 index in our memory, and we can directly search any element in order of one time. So
Okay,
using hashing, we can search any element in order of one
not
time.
one time.
Okay, so this is the basic complexity of the hashing. Okay, but some case is happen in very few times. So for
Mm-hmm.
example, if we are using linear probing, so what is the linear probing approach in hashing? So for example, if we want to insert 43 in our data in our memory, so what this hash function will return? 43 mod 10, same 3
43 mod 10 3. It is
3,
on.
but
Yeah.
3 is already used. So we use the next index. So we check that if next index is free, then we will store this value at next index. Okay, so 43 we will store here.
Sir, if it is full, then
Yeah, so
we.
that is the case where the our complexity will become order of n.
And,
Okay, so for
okay.
example, if we are storing these element like this 3, 13, 23. Okay, this type of thing 53. Okay, uh, so not this is not
Not
possible.
such. I think.
Okay, okay, just cross that. 33, 43, 50, 63, 73. This is possible because 43 will return
Yes, sir.
3.
Yeah, yeah.
Then we will
Mm-hmm.
insert here same things, we will
Mm-hmm.
repeat more 83 and
Mm-hmm.
93. Okay, and if we
Okay.
want to search 93 in
Mm-hmm.
our text, so
It is
we will
on.
use this hash function k mod 10, so it will return 3. Okay,
Mm-hmm.
then we will check this condition, if 93 is available at this position, no.
No.
So that time we will check next position, but
Mm-hmm.
93 is not available at this position also. Same thing here, same thing here. So we have to traverse all the complete all place. Hmm, okay, approx all place.
So
So
the
at
order
the
would be n.
so at this case, the complexity become n,
N.
because we have to traverse all the place.
Mm-hmm.
So this type of situation when occur many few times. So this type of situation called the amortized condition. So in that case, the complexity is this order of n only. So we sometimes we can ignore this. So in hashing, we generally ignore this condition. So we think that this condition is never happen in our computer system. So we can ignore this. So we use this situation as a amortized analysis. Thing. So same things in the respect of BFS. I have to look the lecture completely what actually sir used. So we will discuss this BFS things in the revision session. Right, okay. At that time I
Okay.
will look the topics complete. Okay.
Mhm.
Okay, so
One thing, sir, if
mhm,
all the hash table is full, and if we want to
mhm,
implement some other, suppose all the table is full, right? All the boxes
mhm,
are full, okay,
mhm,
and there is another one that is 106 mod 10.
mhm.
Then yeah, then the result would be 6. So 6 is full. Then where should
Successful,
be
yeah.
that?
So we will same things. We will check the next position.
Mm,
We will check the if we are using a linear probing approach. So there are multiple approaches to used in the hashing techniques. So
okay,
I'm just
okay.
talking about the linear probing approach. In linear probing approach, we check the next position every time. So if you see the some problems we have given in the
Lectures.
assignments, yeah, assignments we have given on the basis of this linear probing hashing things. So I think one more is quadratic probing. So there are some different type of approach we used in the
Mhm.
hashings. So this type of thing is called the collision. If our hashing function returning a address and that address is full already full, so that is
Mhm.
called the collision. So there are multiple approach to resolve this collision. So I'm just talking about one approach, linear probing.
Mhm.
Okay. So according to linear probing, if place 6 is full, then we will check the next location 7. Okay,
Okay.
so that is some approach. So we can resolve this collision things in our hashing techniques. Okay.
Okay.
Okay. So any other query? So only 13 today. Okay.
Sir, mock test can we discuss a question?
We will discuss.
Yeah. So mock test
So
question number 7. I think.
okay. So, okay. 4, 5, 6, and 7. This one? No, no, no.
Yes, sir.
This one.
Uh, yes, sir. This one.
Uh, okay.
Trying to.
7 is lower. Okay. Trying to unlock a box take 10 seconds. Time spent in other activities like picking. So there are two person I think on the basis of
Yes, sir.
this.
6 1.
6
6
and
1.
7.
I had done. But in 7 it was wrong.
Why?
I don't know. Sir, in question number 6, I think my logic is correct. What
Okay.
I
I'm
was
opening
thinking.
the answer. So what's your logic? Can you explain?
Question number 6, what is saying that there are 100 boxes, right? So each boxes is linked with other. Suppose if we open the box 1, then we have to check all the 99 boxes to open the another one, right? Hello, hello, am I audible? Hello, hello.
Yes, yes, you are audible. I think sir's internet has some issue or something.
Okay, okay, okay. Sir, you are not audible. I think your mic is on
Okay.
mute.
Okay.
Yeah, yeah.
Okay. Yeah. So this is scroll. Okay. Yeah. So this is the question. So how you are solving this question?
Yeah. So there is 100 boxes, right? So
Mhm.
for each boxes, we have to open. Suppose we take box 1, right? So take the key from the box 1, and we have to check all the 99 boxes for the unique key for the another boxes, right? And
Okay.
suppose yeah, so we are doing what we are doing in -1 iterations for one boxes. Same wise we are doing for the box 2. Uh, Box 2 we will do in -2 iterations.
Okay.
So it is going for each boxes, it is going in -1, in -2, in -3,
Like
likewise
series.
for
Yeah. Okay. Okay. Okay.
so in into so overall the time complexity would be in into in -1, in -2, like that. So in a square minus in plus some constant, it would be
Yeah. So there is one formula n into n plus one divided by two. So generally, this formula is came up from the sorting algorithms which you used
yes, yes.
insertion sort or selection sort.
Mm-hmm.
So same formula came from these sorting algorithms. So that formula is also come from this problem. So yeah, n into n minus one plus n minus two, like this thing. Okay.
So yes, but
So here. Mhm.
but in question number 7, I didn't do this one. So actually, this was
So
one.
yeah, in this problem, so where we are asking the time actually. So what is the so one if we are one box opening time is 10 seconds. So
Mm-hmm.
total how much time we will spend to collect the gift. Okay. So here the collecting the gift etc. can be ignored. What is the maximum time required in second to collect the gift? Okay, so we will use the same formula. So if we have 100 box and we
Mm-hmm.
are getting the series n plus n minus 1 plus n minus 2 dot 1. So the formula for that is n into n plus 1 divided by 2. So we will use same 100 plus 1 divided by 2. Now this 50. Now 101 into 50. Uh, I think no. So formula is different, I think. So okay, one second. Yeah, color box. So spend the time plus one time. So
So it would be in into
yeah, so
n
if
minus
we
2.
yeah, so series is okay starting from this n minus 1. Okay,
Mm-hmm.
series is starting from n minus 1. So this formula will become change actually. That's n minus 2 dot 1. And then the formula will become n into n minus 1
Minus
divided
1
by
by 2.
2. Then n equal to 100 into 99 divided by 250. Then 0, 95, 45, and then 0 of 45. So this, yeah, 4950. So we are using this formula to calculate the total times.
Mm.
Okay.
Okay.
So yeah, this one is 49500. Only one box is open. So yeah, one box is already open. So we will start from n minus 1. So because of that, this series will be start from n minus 1 to 1. So the formula for this is n into n minus 1 divided by 2. Then we will directly put the value of n and multiply by this 10. Okay. Okay. On other any other person from mock?
Yes, sir. But actually, first I have to do spy on.
Okay. And others, if you have any question from the mock, so we will discuss the mock first, then we will discuss the big five. So if you have any query from the mock questions, you can ask first.
Sir, the question in quiz will be like the mock, right? Means the concept wise.
Same, similar to your graded assignment question, mock question, or if you have access of the previous questions. So already some student created one website for the previous term papers, so you can access the
Mhm.
previous term paper also.
Okay.
Okay, so you can show the exact quiz paper. So question type is similar.
Sir, will you be releasing detailed solutions to the mocks, or we can discuss here?
No, we are not releasing the solution. You can discuss here in the
Okay, sir.
session. You can discuss today, or as well as you can discuss in the revision session also. Okay, so if you have any query in any question, you can ask. Akars, Kavya, Rahul, Bimlesh, Deepak, Geeta, Lakshmi Nandan, Sarthak, Satya. Have you tried this person? All? Okay. Okay, so if you not tried, then first tried, then you can ask in the revision session also. Okay, at that time you can ask others question. So we will revise all the weeks, second, third, and fourth in that session on Friday. So if you have no query, then we will start the week 5 contents.
Sir, week 5 actually.
Hmm?
Week 5, sir, actually, I didn't study.
Oh, you did not start.
No. Preparing for the quiz.
Okay. So no problem. We will just revise the concept.
Okay.
Just see the concept. So uh, after the quiz, you have to submit the assignment.
I think.
Okay. So in the continuation of the graph topics, so week 5 is also covered the some topics related to the graphs. So there are basically two topics we are covering in the week 5. First is
Mhm.
shortest path and second is spanning tree. Okay. So first, starting this topic, we have to see that how we can represent the weighted graph. Because here we are using the weighted graph for the shortest algorithm and minimum spanning tree algorithms. So first things, how we can represent the weighted graph in our Python program. So we are using two different way. First is adjacency matrix representation, and second is adjacency list, like a previous week representation. But here we are using the weight information also with every edge. So for example, here some edge are given for so this is the edge. So this is for the directed graph. So first we are seeing that the directed graph weighted, which is weighted. So here first is the source vertex where the edge coming from, and second is the target vertex, and third value is representing the weight on the edge. So this is the all edge which we are representing the by the variable dh. Second is the size of the size of the graph. So here 7 value is representing the total number of vertices in our graph. After that, we are just using numpy. We can create this matrix using numpy, as well as we can create using nested Python list. So using numpy, we are creating a zero matrix of size, three-dimensional matrix we are creating. uh, So this is representing the row, this is representing the column, and this is the third dimension. So every row column combination contains the two values basically. So first value, so we can access these value using three index I, J, and W. Okay.
Sir, can you repeat the line number 4? What is the significance of 2 here?
Significance of two is actually at every place we are storing two value.
At every column,
Every
each
row and
column.
column combination.
Okay.
Okay. So for example, if we are storing, yeah. So this is our matrix. 0, 1, 2, 3, 4. For example, we have a 5 vertex. 0, 1, 2, 3, 4. So these are representing row, these are representing column, and every crossing points we are storing two values. So for example, this is for first value, this is second value using comma. So size of this column is 2. Okay. So here the first value is representing that edge is exist or not. So if this value is 0, that means there is no edge. If this value is 1, that is representing there is an edge, and then we will store the weight of this weight of that edge in the second place here. Okay. So this is the representation. So if you see that, so for I, comma J, comma W, so we are reading this list of tuples, and every tuples contains three values. So we are reading this three value in I, J, comma W, and we are storing these value in our each row and column combinations. So for row and I, comma J, so these are representing the row and columns, and this value is representing the first value and second value, 0 and 1. So if edges exist, we are just storing this 1, and not exist, so that value will be by default is created as a 0 using numpy. So we are just storing the edge information here. So first value is 1, and second value W is representing the weight of that edge. So here one adjacency matrix is created for this graph using numpy.
Sir, can you write this on paper? I mean, how it is going on? Line number 6 and 7.
Okay, one sec. I'm taking this code on the. Okay, so here the size of matrix is 7 by 7. So 0, 1, 2, 3, 4, 5, 6. Same thing, 0, 1, 2, 3, 4, 5, 6. So initially we are creating this all the matrix with the size 0 matrix we are creating using numpy. So all information is 0 like this. Okay.
Okay.
So every place we are storing this by default value 0, 0. At in this line we are reading this list dh, and we are reading these tuples in I, J, and W. Okay. So I is first value, J is second value, and third is W is this 10 value. Okay. So this is representing that there is one edge from 0 to 1 with weight 10. So this 0 is starting node is representing by this row. This is representing by I. This is representing J. So I to J. So 0, this is 0, and 0 to 1. So this is this place. Okay, 0 and 1. So we will update that the position that these contain two value. So this is the index of first value is 0 and second value is 1. So we are just changing this Wi, comma J, comma 0 by 1. So we are updating this field is 1, and what is we are reading in W is 10 for the first is 10. Okay, so in second place we are just updating this by 10. So this contain the information of one edge, that is this first one. Same thing 0 to 80. So 0 and 2. So this 0 to 80, 1, comma 80. it will be updated. Same things for third edge, 1 2, so 1 and 2, so this position 1 comma what is the weight is 6. Okay, and 1 4, so 1 4, this will be updated like by the 20. Okay, and 2 370, so 2 370 here, 2 so this is 1 and comma 70, this position. So all edge will be updated in our matrix 4 5 50, so 4 and 5 here 150, and 4 6 5 4 6 5, so this is 1 5, and 5 6 10, so 5 6 10, so yeah, 4 6, yeah, okay, 5 6 1 comma 10. So the other remaining value will remain the 0 0. Okay, so 0 0 0 0 like this. So we get one this matrix that contains the information of all edges with weights. Okay, so this is the adjacency matrix for weighted directed graph. And second representation is adjacency list representation for the graph. Here we will use the dictionary. Okay, so same things, we have these as if we represented that in our page. So okay, now this time same as we want to represent in our Python using dictionary. So here we are created one dictionary here, WL empty dictionary. After that, that's for I in range size. So size is 7. This is representing total number of vertex 0 to 6. And WLI. So for each vertex, we will store this information. How many edge are connected. So WL, for example, WL. So for I in range size is 7. So that value will be start from 0 to 6. So first value will come here 0. Okay, and then we are in the first loop we are initializing with empty list for every. Okay, so WL1 empty list. Same thing. For each vertex we are initializing with empty list 6. So this is happening by this 2 lines. After that, we are reading this all edge information from this D edges list, and in each tuples we will check that what is the value of first index in the tuples. This is 0. So at this position we will store that append j comma d. Okay, so we are appending this j comma d in this empty list. So for example, for the first edge 0, so we will append that this 1 comma 10 here. So 1 comma 10, this is one edge representation. Okay, and same things. So for example, if we there is for the second edge 0 to 80, so this is also starting from the same 0 vertex. So we will append in this, yeah, so 280 like this. Okay, so we will store this edge information in this format in dictionary. So that is called the adjacency list representation. Okay, so we can access that what is the adjacency vertex of 0. So we can find directly from this. We can read this key in the dictionary 0, and we can directly find that. So how many edges are connected from 0 is 2, 1 and 2. And what are the weight of these edges? 10 and 20. We can directly access this information. Okay, so this is the representation of directed weighted graph in our Python programming language. So there are two ways. First is adjacency matrix, and second is adjacency list. So after that, second is weighted undirected graph. So same things in the undirected graph. So edge is considered from the both sides. If there is one edge between two vertex, so for example, in the undirected graph, if we have a vertex A and B, and there is one edge, okay, and there is one weight 50 here. So we will store this a. Okay, I'm just taking 0 and 1. Okay, if we are creating the representation adjacency matrix for undirected graph, then this 0 and 1, in that position we will store that 1 comma 50. Same things. So here, okay, so this is uh, 0, 1, 2, 3, 4, for example, 1, 2, 3, 4. Okay, so this edge is considered from this 0 to 1, as well as this edge will consider from 1 to 0, because there is no direction on the edge. So we will represent this edge from both place. So 1 to 0, here we will also represent that 1 to 50 in the undirected graph. In the directed graph, we just represent from source to destination, but here there is no source, there is no destination. Edge is connecting two vertices, so we will represent at the both place this information in our matrix. So one edge is represented by two value in our matrix, two position. So same for the adjacency list. So for, if we are creating a adjacency list, so if D our dictionary, and we are just we are storing this information D0, and in our matrix we will store that there is one matrix, so D0 to D1 and 50, and same times we will store this information from for 1 also, so 0, 50. Okay, so for representation we store two times this information for each vertex which are connecting by the edge. Okay, because of that, here we are doubling this edge information. If our edge is so this is the direct edge, and we are just changing double of this size, so dh plus. Here we are changing the order of source and destination. So here I and j, and here we are changing this j and I. Okay, so we are getting information for this edge from both vertex side for the undirected graph. Same things for the list representation for undirected graph. So we are creating edges from both vertex, 0 to 1 as well as 1 to 0. After that, we are representing edges in the same manner as the previous. So this is the representation of directed weighted graph and undirected weighted graph. After this representation, so for any algorithms, we will receive this information for the graph, and then after we will use this representation to solve our problem for the graph. So first topic is shortest path. So shortest path is a commonly used topic in our life. So if we see the Google Maps, so there is a basic common application we generally used. So if we are planning to traveling for any place, and if we want to find the shortest way or shortest path for the destination, so we can use Google Map. And how Google Map provide this information to us, so we can use the shortest path algorithm to solve this type of problems. So if we have a multiple path from any source to destination, so how we can find the shortest path among all the paths. So there are two. First type of the shortest path is single source shortest path algorithm. Here we have a source vertex information, and we want to find the shortest distance for every node, every other nodes in our graph. So this is called a single source shortest path algorithm. Here source is one, and other are all vertex are destinations. So we will calculate the shortest distance for every other vertex. So this is the first category of the shortest path, single source shortest path. And to solve this problem, we will use these two algorithms, Digest algorithm and Bellman-Ford algorithms. So first is Digest algorithms. So these are some important points to find the shortest path of using the Digest algorithm. First thing, Digest algorithm works for both directed and undirected graph. Okay, so these are some important points you should know. You should remember these points for exam purpose. So Digester algorithm works for both directed and undirected graph. Second point is Digester algorithm doesn't work for graph with negative weight or negative weight cycles. Okay, so if our graph contains the negative edge weight, so this Digester algorithm may be written wrong answer in some case. So we can say that this is not always correctly work on the negative weights or negative weight cycle. So what is the negative weight cycle is here uh, in graph? Can anyone tell me what is the negative weight and negative weight cycle?
In a cycle, if some of the weights become negative.
So for example, if we have a starting node A, B, C, and D, okay, and if we have a, okay, I'm just talking about directed graph. So 2, 5, 3, and -2. Okay. Okay. So tell me, is so this graph have any negative weight cycle or not?
Yes, BCD.
B, C, D. Okay. So how we can find that the graph have negative weight cycle is if we start from any vertex. For example, if we are starting from here, okay, so if we are moving B to C, then we are getting this 5 weight. After that, C to D, so 5 minus 3 is 2. Then D to B, if we are returning on the same vertex where we were starting from, so -4. So what is the total value is, so 5 minus 3 minus 4 is -2. So if we get the negative weight in the cycle after moving all the cycle, all the cycle path, so if we are getting this negative value, so that is called the negative weight cycle. If we consider that this A, B, C, D, A, is this negative weight cycle? A to B to C to D,
No.
A. Okay, this is also a cycle in our graph, but this is not a negative weight cycle. So here we are starting from A, so 2 plus 5 minus 3 minus 2. Okay, so this is total weight is 2. After moving on the all the path, we are getting 2 positive values. So this is not a negative weight cycle. So there is two condition. First is negative weights, just use the terms negative weight, and second is negative weight cycle. So both are the different things. So negative weight cycle, so digester algorithm works. Digester algorithm doesn't work for graph with negative weight as well as negative weight cycle. Okay, so it may be in some case it can return the correct answer, but not always. So if it is not returning the correct answer in all cases, so we can say that it doesn't work. Okay, so and next point is this algorithm return the shortest distance from the source to all other nodes, but after some modification like maintaining parent information of each node, we can find out the shortest path also. Okay, so algorithm is just return the shortest distance from source to all destinations, but we can also find the path using the parent information addition. So if we see this graph, how we can apply this algorithm on this graph. So I'm not using the implementation part on this graph. We will just apply this algorithm using the dry run. Okay, I'm taking this graph in our page 1 second. Okay, so we have one graph, directed graph, and we want to find out the shortest path using digestion algorithm from there. So for example, if we have a source vertex 0, okay, so this is our source vertex. So what we will do in our digestion algorithm is, first we will initialize some value. So we will use two metrics. First is visited. What is visited is, so we will mark that if our node is visited, we will mark that visited is equal to true, or we can use any value for that. And second value is, we will update the path distance, shortest distance on each node every time, and we will update this shortest distance value if we find more shortest path compared to the previous path. So we will start from the initialization part. First we will initialize this uh, second value. What is the value parameter is in our algorithm is, this color is not working. Yeah, so visited and distance. Okay, so I will take the same parameter. Yeah, second is distance. Okay, so these two variable we are using for each vertex. We can just represent that 0, 1, 2, 3, 4, 5, 6. Okay, so we will represent this value in the graph at the same place. So initialization is that at the source vertex we will mark that distance is 0, and the remaining vertex we will mark that the distance is infinite for each vertex. Okay, this is the initialization part. And initially visited vertex, we are starting from 0, so we will mark that this is true and remaining is false. And this is 0 and this is all infinite. Okay, so this is the initialization part of this algorithm. After that we will find out that so we will start from the source vertex, and then we will check in our matrix representation what are the adjacent of the source vertex. So we will start from the source vertex 0 and check that what are the adjacent node of this source. So what are the adjacent node is, where we can move 1 and 2. We can directly move on these two vertex by direct edge. So we can move on 1 and we can move on 2. So what are the previous distances initialized is infinite and on 1, and what we are getting new distance is 10. Okay, so 10 is less than the previous distance value. So at any time if we are getting the less value compared to the previous value, so we will update this information on the distance value of vertex. So here the previous value is infinite. Now we are coming from the source in the 10 distance, so we will update that by 10 here. Okay, same things for the 0 to 2. Last previous value is infinite, and we are coming from 0 to 2 by 80. So this 80 is less than this infinite value, so we will update this value by 80. Okay, so now these two value is updated in our table, and we can mark this information here. So in the first checking, so we have updated this information like 0 and 1 is, this is 10, this is 80, and remaining is infinite. Okay, now we will check that. So this 0 have already visited, marked as a true, but other are remaining vertex are not visited. Now we will check that which vertex contains the minimum distance value, which are not visited. Okay, so not visited vertex are 1, 2, 3, 4, 5, 6, and the minimum distance value is 10, and this is the vertex 1. So we will select the vertex which contains the minimum distance value which are not visited. So we will select this one. Okay, and now we will check that where we can move this from this one node. Okay, we will check only for that node which are not visited. So we can move from 1 to 4 and 2. Okay, so now the weight, now the distance on this vertex is 10. So we will add this distance in the next edge value. Okay, because we are considering the path from the source 0. So we will add this distance in the next edge value. So from 1 to 4, so the total edge value is 20, and we will add this 20 into this 10. So 10 plus 20 is 30, and the previous distance on the 4, on the node 4 is infinite. So this 30 value is less than this infinite. So we will update this value by 30. Same things. If we are moving from 1 to 2, so we can move from 10 plus 6, 16, and the previous value is 80. Okay, so we are getting the last value compared to the previous one, so we will update this is by 16. Okay, so we will store this information. So now, and we will also mark that the one is visited now. Okay, so we will mark that one is visited. So we can also just represent that this is part is done. Now from 1 we are moving to 4. So 4 distance will be updated in that case. So this is 4, now this is 30, and 80 becomes 60, and remaining is infinite. Okay, now our unvisited vertex are 2, 3, 4, 5, 6. Now the what are the, which vertex contains the minimum distance value? This is 16. Okay, this is 2. So we will check that this 2 now, and we mark that this as a visited, and we will check that where we can move from this 2 is the only one vertex we can move. So 2 to 3. Now so distance till 2 is 16, and 2 to 3 is 17. So total is 86, and 86 is lesser than this infinite value. So we will update this 86, and so this is this is selected, and now 3 contain infinite, this become 86, this is remain 30, infinite. So in this process, so only one updation is happening on node 3. Now we will repeat this process again. We will select the next minimum vertex is 30, and this become 2. So same things for this 4 vertices. So we are here now. Now we can move from 4 to 5 and 4 to 6 directly. So if we are moving from 4 to 5, so 30 plus 50 is 80, and which is less than this infinite value 80. And if we are moving from 4 to 6 is, so 30 plus 5 is 35. So this is also less than infinite, so 35. So if we are selecting this, so this 86 remain 86, this 5 become 80, and this 6 become 35. Now next selected vertex is 35. Okay, this one. So here we can not move from on any vertex. So this step will be skipped without any updation. Now we will so there is no update. 86 and 80 also become 2. Yeah. Now we will select the next 80. So 80 is 5. So we can move 80 to 5 to 6 first, but the distance 80 plus 10 is 90, but the previous distance is 35. So we will not change it. So it will remain okay. So this we have already visited. Okay, so we will not check that. Okay, so there is no update after that. So now 86. So we will select. So there is no vertex is remaining unvisited. So this is the complete process of digest algorithm. If you will see that the shortest distance from 0 to every node, so we can move from 0 to 1 in 10 distance. So this is the final result. Okay, so 0 to 1 we can visit in the 10 distance, 0 to 2 we can visit in the 16 distance, 0 to 4 we can visit in 30, 0 to 5 we can visit in 80, 0 to 386 and 0 to 6 is 35. So this is the shortest distance from 0 to all vertex. So this is the information regarding the shortest distance. And if we want to find out the shortest path, so we can contain the parent information uh, in this algorithm, and we can find out the shortest path also. So what is the path information? Currently we are getting the just the information of distance. So if we are checking that what is the shortest path distance for 6 is 35, but we cannot return the exact path by using this information. So we will contain one extra parameter for every vertex. We can say that parent. Okay, so every time when we are updating the distance, if we are getting the smaller distance compared to the previous distance, and we are updating the distance, so at that time we can store the information of the parent node where we are coming from. So for example, if we are starting from this 0 to 1, okay, so initially this value is infinite, and we are updating this by 10. So 10 is smaller than infinite, so we are changing this value. So at the same time we can contain the information what is the parent of 1 is. So where from we are getting this 10 value. So we are getting this 10 value from node 0. So we can store this information in our another matrix. So for example, if we can create a dictionary for that, so we can create this information like so for example 0 1 2 3 4 5 6. So this is the key of each vertex, and for 0 this is the source vertex, so there is no parent for that, so we can directly store that none. And for 1, so we are updating this 1 distance from 0. Okay, so we will contain that this is the 0. What is the parent of 1 is 0. Same for 2. So initially in the first step we are getting this 80 value from 0. So the parent of 2 is 0. But after the second step, when we are selecting the vertex 1, so we are getting the distance 10 plus 6 16, which are also smaller than this 80. So we are updating once again. So we will update the parent of 2 is by 1. So we will update this by 1. Okay, so we will update the parent information every time when we are updating the distance, if we are getting the smaller distance by the previous one. So we will calculate the parent for each vertex. So for example, for 2 we have calculated. For 3, so for 3, so 10 plus 20 is 30. So 30 we are getting from 1. So parent of 3 is also 1. And what is the parent of no, this is 4, sorry, 1. For 3, the parent for 3 is 16 plus 70 86. So this is 2. Okay, what is the parent for 5 is
4.
4. Okay, and what is the parent of 6 is 4.
4.
Okay, so after getting this information you can find out the path for any node. For example, if you want to find the path from 0 to 6, what is the shortest path from 0 to 6 is? So you can start from the destination vertex. So we are interested to find out the shortest path from 0 to 6. So we will start from the 6 and check that what is the parent of 6 is. So what is the parent of 6 is 4. We will move to the 4 and then check what is the parent of 4 is 1. Okay, we will check the parent of 1 is 0. Okay, so this is the path. If we follow this path, we can reach from 0 to 6 in 35 distance. So in the reverse direction, if we can visit, we can access the information of parent of each vertex. We can find out the path also. Okay, so this is the concept of digest algorithms. If you see the code, so we are doing these things in the code. So yeah, adjacency matrix. Yeah, this is the digital algorithm. So if you see that this is the row matrix, this information we are getting from what is the shape of our matrix is. Second thing is infinite. So we are just calculating the largest value which are not possible for any weight. Just we are multiplying this. Otherwise, in Python, you can directly assign the infinite value. If you write the float inf string, if you write the in Python, we can directly assign the infinite value like in this form. So float, and inside the float, just inf in the string format. Just write this. So infinite value will be assigned to your variable. So you can directly use this syntax to assign the infinite value. Otherwise, sir, just calculate the one largest value which are not possible by for any weight for any on any edge. Okay, so this is the infinite value we are assigning the on the variable infinity. So we are taking these two parameters, visited and distance for each vertex. Initially, we are initialized by false for each vertex and infinity for each vertex. So distance for each vertex is infinity and visited mark as a false. After that, we are starting from the source node. So we are initialized, we are changing the distance for source node is 0, and we will update the information now in the next loop for u in range rows. Okay, so here we are just calculating that which node is the which node contains the minimum distance value. So you in the line number 11 we are getting this information which node contains the in line number 11, 12 and the others things also. Yeah, line number 1, 2, this one 15. We are getting this information which node contain the minimum distance. Okay, we are removing this node from our list. After that, after removing this node, next b, we are just marked that this next b is true. Now this is visited. After that we are checking the adjacent node for v in range call col. So this is the we are just accessing our adjacency matrix, and we are just checking that what are the adjacent node of our vertex is, and we are just updating the value of each vertex for each adjacent vertex. So if the previous distance and the updated distance, so which is the minimum value? Okay, so we will update on that vertex distance. So we are repeating this process for each vertex. So finally we will got the minimum distance for each vertex. So you can write your own code. Doesn't matter. You implementation can different. If you see the implementation from a different resource, so you will get the different types of implementation. But the concept should be same. Concept should be follow, which we have discussed in the example. Otherwise, you can implement your own algorithms on your implementation. Okay, so this is the digester algorithm concept to find the shortest path. And this is the second version using the W list, adjacency list. So now next algorithm is Bellman-Ford algorithms. So say some important points we will discuss. So Bellman-Ford work for both directed and undirected graph with non-negative edge weights. So here both directed and undirected graph with non-negative. Non-negative means positive weights. So we can apply this algorithm on directed and undirected graph with positive weight edge. But Bellman-Ford does not work with an undirected graph with negative edge weight. So undirected graph. Okay. So for undirected graph with negative edge weights is also considered as a negative weight cycle. So for example, if you have a node and second node is B. So this is undirected graph. And if this S contain negative value, so we can say that this is also containing negative bit cycle, because we can move from A to B, then B to B can come back to from B to A. So the total distance becomes 10 minus 10. So that will become minus 20. So for undirected graph, negative edge weight also considered as a negative weight cycle. So we can also not apply this Bellman-Ford algorithm on undirected graph with negative edge weights. Okay, but directed graph we can apply. So for example, if for directed graph, if this edge contains this minus 10 weight, so this is a negative weights, but not, we cannot see that this is a negative weight cycle. So we can apply the Bellman-Ford algorithm on this type of graph. So Bellman-Ford does not work with an undirected graph with negative edge weight, as it will be declared as a negative weight cycle. So this is the same thing. So Bellman-Ford work for a directed graph with negative edge weight, but not with negative weight cycles. Okay, so Bellman-Ford we can apply on the graph which contains the negative edge weight, but not negative weight cycle. But in digester algorithm we cannot apply, because we never in the digester algorithm we never look the nodes which have already visited. Okay, but here we will look again that vertex. So how the algorithm works, we will see that dry run. And second. Okay, sorry. Okay, so this graph contain many negative weights, but I think no negative weight cycle is in this graph. Just look at -2. Okay, there's no cycle. So there's one cycle from here, 2, 3, 4, 5. Okay, but this -2, -3. Okay, this is also not very negative weight cycle. Okay, so this graph contains the negative weighted edge, but there is no negative weight cycle is in this graph. So we can apply the Bellman-Ford algorithm on that graph. So what is the concept of the Bellman-Ford algorithm is? So initially same things, we will initialize with all the distances infinite. Here we are not marking these things if our vertex is visited or not visited. Okay, so we will apply this process total number of n vertex times. So for example, if we are apply this algorithms, so first how many total number of vertex in this graph is? So 1, 2, 3, 4, 5, 6, 7, so 8. Total number of vertex are 8. So we will repeat this process 8 times, and every time we will check, we will start from this 0. Okay, and check that what is the minimum distance from this 0 is 0 to 7 is. So initially all are infinite, so this is source node 0, and this is infinite, all are infinite. Okay. Now we will update these weights. Now 0 to 8, we will update this 8 information. 0 to here on the 1, so we will update this by 10. Now by the second, so if we are coming, so here we are not selecting any minimum distance things, so we will check that on the one vertex. So now we are starting from the 10, so we can move from 1 to 5. Okay, so we can only move 1 to 5. So 10 plus 2 is 12. So this is lesser than the previous value, 12. Okay, same things we will now we will check from the next vertex. Okay, according to the algorithm, we will, I think we will digit by column by column. So for I in range rows, okay, for U in range, then B in range columns, and mark that one distance we will update to minimum. Okay, yeah. So we are traversing the vertex according to the vertex number. So we are starting from 0, then we 1, then we will check from the 2. So what is the next we where we can move from 2 is 2 to 1 and 2 to 3. Okay, so what is the value of at 2 is infinite. So 2 plus infinite plus 1 is infinite, which is greater than the previous value. We will not update this. And infinite plus 1 is infinite. So this is also infinite. So there is no change if we are checking from 2. Then we will check from 3. So also there is no change. So infinite plus 3 is infinite. Same things for the 4. So infinite minus 1 is also infinite. And the previous value is 12. So we will not update this. And next is 5. So 5 to we can move to 2. So here the value is 12 and 12 minus 2 is 10. So now this value will be updated. So this become 10. Okay, now we can move from 5. No, we cannot move from anywhere. Now we will check the 6. Now from 6 we can move to 1, but the value at 6 is infinite. So there no update will be happen from the 6. Now the 7. So 7 to 6 we can move. 8 plus 1. So this value will become 9. So this is the first cycle we have repeated. Now same things we will repeat again. So we will repeat this process. Total number of vertex times. So total number of vertex is 8. So we will repeat this process 8 times. And second times we will check again. So if we see that 0 to 1, so now the value is 10. So which is also 10. So there is no update. Now 0 to 7. So 8. There is no update. Now we are checking from 1. So 1 to same things. There is no update from 1. Now we'll be checking from 2. Yeah, so now the update will be happening. So 2 have 10 value. Okay, now 10 plus 1 is 11. So now this value will become changed 11. At 3, so 11 plus 3, this will be changed. 11 plus 3 is become 14. Now from 4, so 14 minus 1 is 13. So now the previous value is 12. So we will not update this. Now 5 is 12. 12 minus 2. So this will remain same. Okay, so there is no change. And from 6, this is 9. 9 minus 1 is, yeah, so now this time value will be updated. So 9 minus 1 is 8. So this become 8 from 6. And if we see the 7, so 8 plus 1 is 9. So there is no. So this is the result from the second cycle. Okay, so we will repeat this process 8 times. Same process we will repeat the 8 times, and we will get the shortest distance from 0 to every node. Okay, so here we are looking the vertex which have already visited. So we are not marking that this information if node is visited or not. We are just repeating this checking process total number of vertex times. So after last loop, we will get this shortest path information. Same things we can contain the parent information in this algorithm also, and we can find out the shortest path information from here. Okay, so you can apply the algorithm 8 times. So definitely you will get the shortest path for every vertex. So this is the concept of Bellman-Ford algorithms. So if you see the algorithm, so we are repeating the same process in these algorithms. So this is the first loop is contain the total number of vertices. So here rows is representing the total number of vertices in the graph. After that, for each vertex, we are checking that how many adjacents are available for each vertex, and we are updating the distance if we are getting the smallest value. So we are repeating this process. Finally, we will get the shortest path information. So this is the two algorithms which we are using for single source shortest path. Okay. Now the next algorithm is all pair shortest path. All pair of shortest path. So here the meaning is that all pair of shortest path, we will apply this algorithm and we can find the shortest path between any pair of node vertices. So in the final result, we will get the information, the shortest path between any pair of vertices. Okay. In the previous one, we are just getting the information, the shortest path from particular source to other vertex. But here we can find out the information, the shortest path between any pair of vertices. So this is called the all pair of shortest path algorithm. So there is one algorithm, Floyd-Warshall algorithm. So find the shortest path between every pair of vertices I and j. It is equivalent to if run digestal or Bellman-Ford from each vertex. Yeah, so this is the equivalent. So yeah, this all pair shortest path algorithm means if we are applying the Diastaya or Bellman algorithm on every vertex one by one. So what result we will get? We will get by this using this Floyd-Warshall algorithm directly. Okay, so these are some important points. So Floyd-Warshall works for both directed and undirected graph with non-negative as weights. Okay, so same things like as a Bellman-Ford algorithm. So same points are coming here. So we can apply this Floyd-Warshall algorithm on directed and undirected graph with positive as weights. Same things, Floyd-Warshall does not work with an undirected graph with negative as weights. Okay, so because of that, because in undirected graph, negative as weight considered as a negative weight cycle. So we cannot apply this algorithm. Floyd-Warshall algorithm is an alternative way to compute transitive closure. So transitive closure is a different thing that represent the path information. Is there any path available from vertices I to j or not? Okay, that is called the transitive closure. If we get this information, so here the transitive closure bk. So this I comma j equal to 1 if we can reach from j from I. So this transitive closure is basically provide this information if is there any path available from node I to j or not. Okay, so we can find this transitive closure using this Floyd-Warshall algorithm concepts. And Floyd-Warshall works for a directed graph with negative as weight, but not with a negative weight cycle. So these points are very important and commonly asked in the exam. Okay, and formula for Floyd-Warshall algorithm is given below. So this is the important formula which is used in this Floyd-Warshall algorithm. Okay, so now this is the code, but we will use the we will check the concept. What is the concept? So because the calculation is too much in this Floyd-Warshall algorithm, so we will take some smaller graph. So for example, if we have a graph 0, 1, 0, 1, 2, 3. Okay, so we have the graph. So for example, 2, 5 minus 1, Okay. Okay, so I'm just taking the small example for that, and we will check that how we can solve this problem using Floyd-Warshall algorithm. So this is the initial graph, and we want to find the shortest path, uh, all pair shortest path using the Floyd-Warshall algorithms. So we will create the matrix for that. What is the matrix? So we can directly represent the matrix. So this is the base matrix for the graph. So we can represent this matrix by k0. Okay. So here 0, 1, 2. So there are total 3. Okay. So 0, 1, 2, 3. So this is I. This is j, and we will directly retain this information. So 0 to 0 is 0. So here 0 is representing that on the same vertex, and infinite is represent that no path is available. 0 to 1 is 2. 0 to 2 is 6. 0 to 3 is there is no h, so we will represent this infinite. And 1 to 0 is 1 to 0 is there is no finite. 1 to 1 is 0. 1 to 2 is 3. So 1 to 4 is, so 1 to 3 is 5. Okay, so now 2 to 0 is infinite. 2 to 1 is infinite. 2 to 3 is 4. Sorry, 2 to 2 is 0. 2 to 3 is 4. And 3 to 1 is -1. 3 to 0 is -1. 3 to 1 is infinite. 3 to 2 is infinite. So this is the initial matrix. Okay, and we will apply the Floyd-Warshall algorithm formula. What is this formula is? So if we see the formula, so this is the formula. Okay, this is image actually. Okay, so we will write this formula. So what is this formula? Okay, so this is the K0 matrix, and we will check. We will. So we are just writing the formula. What is the formula? So K here K. If we represent this D, this is the matrix D, and this is the 0 is represented by this K. Okay, so K value is 0. So here D K, and K are representing from 1 to 4, and I comma J equal to min of D I comma J in the matrix of K minus 1 comma D I comma K plus D K comma J. But this is taking from K minus 1 and K minus 1. Okay, so this is the formula for Floyd-Warshall algorithm. This is the general formula. The representation can be different in the formula. So this K is represent the matrix number here. Okay, so here this is the base, first matrix we are just created using the graph, and after that we will create the second matrix. So here the next value is 1. So we will calculate the value of D1. That means we are creating the second matrix. So for example like this, so we are creating a D1 matrix here. 0, 1, 2, 3, 0, 1, 2, 3. Okay, this represent I, this represent J. Now in the second case, so we will calculate the value of each position here. So from the first matrix, okay, so we have a one matrix D0. We will calculate the second matrix, and we will calculate the each cell value using this formula. Okay, so for D1, so here K value equal to 1. For this complete matrix, K value will remain the 1. Okay, K value will remain the 1. and we will calculate the value of I comma j. So this we are calculating the value for this position. So I is 0 and j is 0. Okay. So I equal to 0, j equal to 0, k equal to 1. We will put this value in our this formula. So now it become like, so d 0, k minus 1, 1 minus 1 is 0, and I is equal to 0, 0, comma d 0, 0. So I is 0 here, and k is our 1, 0 comma 1, and plus d 1 comma 0. So we will apply this formula for every position, for calculating every position, and which value is coming less. So basically what we are doing in our graph, so we are just checking that for 0 to 0, so there's no meaning for this 0 to 0, but if we are calculating the distance for 0 to 1, okay, so this is also a not clearing concept. So if we are, for example, if we are calculating the shortest distance for 0 to 2, for example, this position, so first we will check that is there any direct edge is available 0 to 2 using this value. So I to j directly 0 to 2, what is the weight? Weight is 6, and using through the node 1, what is the total distance through the node 1 is. So if we are moving from one vertex, so for this matrix we are coming from one vertex every time. So first we will check the direct distance, and second time we will check the distance through one vertex. So 2 plus 3, so this is 2 plus 3 is 5, so this value will become 6, and this will become 5. So which is minimum is 5. So we will update this information in second matrix 5 here. Okay, so we will apply this formula for every combination. So for 0 to 3, first we will check that is there any direct edge is available 0 to 3. So no. So previous edge is infinite. If we see that the distance through vertex 1, so 0 to 1 and then 1 to 3. So 2 plus 5 is 7. So we are getting less distance by the direct edge. So previous is infinite. Now we are getting 7. Okay, so for each combination, we will check that is there any direct path is available, or is there any path available through vertex 1. So we will calculate all the field value for this matrix D1. Same things we will repeat. Now we will check that D2. This is matrix. Now, so D2 represent that. First, we will check the direct distance from I to j is minimum, or I to k, then k to j is minimum. Which one is minimum? So we will update this information using the help of this previous matrix D1. Okay. For computing this D1, we are taking the value from the previous matrix D0. For computing the D2 matrix, we will use the information from D1. So same things we will repeat 4 times because we have a 4 vertex in our graph. So in the last matrix D4, we will get the shortest path information for each pair of vertex. So this is a little bit large computation manually. So for example, for this graph, so 1 2 3 4 5 6 7 8. So for 8 vertices, if you can, so this is very difficult to calculate manually for using this Floyd-Warshall algorithm. So 8 matrix, you have to create 8 by 8 size of matrix 8 times. You can think about this total 64 into 8 calculation you have to done by this formula. So we are applying this formula using these 3 loops here. So you can see that the complexity of this algorithm is NQ. So first loop is k in range, first total number of vertices, second loop, then third loop. Then we are applying this Floyd-Warshall formula. Okay, so finally the final matrix will return the all pairs shortest distance value. So code is simple, but the manual calculation is very tough for this Floyd-Warshall algorithm. Okay, so the complexity become order of n to the power q for this. So this is the all pair shortest path algorithm. So the main important thing in Floyd-Warshall algorithm is this formula. So this is the shortest path algorithm. After that, we will come on the spanning tree. So what is the spanning tree? Basically, so if we have a connected graph, okay, so we will convert this connected graph into a connected tree. So what are the some important points for the spanning tree is retain a minimal set of edge so that graph remains connected. So we will remove the edge from the our original graph, and then we will convert that graph into a tree. So tree have some definition. So in tree there is no cycle is possible. So after removing the edge, so the minimal set of edge so that the graph remains connected. Graph remains connected after removing on the edge. So that is called the tree. Recall that a minimal connected graph is a tree adding an edge. So after creating this tree, if we are adding any edge in our graph, so that will definitely create a cycle or loop. Removing an edge disconnect the graph. So after in from this tree, if we are removing more edge, then definitely the graph will become disconnected. Want a tree that connects all the vertices called the spanning tree. More than one spanning trees in general. So for example, if we see that, for example, if we have a graph, so here A, B, C. So this is a simple example D. Okay, so if we have a graph, so I'm also assigning some weights 2, 3, 5, 6. Okay, so this is a graph, connected graph. And if we want to convert this a spanning tree, so we can remove any edge, but graph our graph should our tree should remain connected. All vertices are remain connected. So how many edges we can remove from this graph is only one. So for example, if we are removing this edge from this graph, after that we cannot remove any edge from the graph. So after removing this two, we will get this A, D, and B, and C. This one. Okay, so this is a original graph, and this is called a spanning tree. Spanning tree. Because if we are removing any other edge from this spanning tree, so then the graph will become disconnected. So for example, if we are removing this one, so graph will become disconnected. If we are adding any extra edge in this graph, so definitely it creates a cycle. Okay, so we can say that this is a spanning tree. So we can create many so for any graph we can create a many number of spanning tree. So for example, if we are not removing this two, we are removing this 6, so we will get different types of spanning tree. So A, B, C, and D. Okay, so in this case 6, 3, and 5. In this case 2, 3, and 5. Okay, this is also a one spanning tree for this graph. And if we are removing others, so for example, if we are removing this 5, so we will get this A, B, C, and this D. Okay, 2, 3, 6. So these all are spanning tree for this graph. So I think one more possible also there. So there are many possible spanning tree for any graph, but here we are not interested in spanning tree. We are interested in minimum spanning tree. So what is the minimum spanning tree is? So minimum spanning tree is if we are creating a spanning tree for any graph, and if we are adding the weight of each edge in spanning tree, so the total edge weight should be minimum for a spanning tree in all possible spanning tree. So for example, if we are adding the total weight for this spanning tree is 6 plus 5 plus 3, this is 14. If we are adding the weight for this spanning tree 2 plus 3 plus 5, so this is 10. If we are adding for the weight is 6 plus 2 plus 3, so 6 plus 2 8, this is 11. Okay, so more possible spanning tree are there. So the spanning tree which contain the smallest total distance, total weights on the edge, that is called the minimum spanning tree. So for example, in these three, if these are the all possible three spanning tree for this graph is, so we can see that this is the minimum spanning tree. So this is called the minimum spanning tree. So minimum cost spanning tree, add the cost of all the edges in the tree. Among the different spanning tree, choose one with minimum cost. So all the spanning tree, we will choose the minimum cost spanning tree. Some facts about trees. So in a tree, if total number of vertices are n, so definitely edge will always n minus 1. So if total number of vertices are 4, so definitely in a spanning tree, the total edge will be 4 minus 1 is 3. So this is the one fact in the tree. So the tree terminology we will also learn in the week 6, but some terms is coming in the week 5 also, because we are also learning this concept spanning tree. Adding an edge to a tree must create a cycle. In a tree, every pair of vertices is connected by a unique path. So if you see the spanning tree, so you can see that if you choose the two vertices in the spanning tree, so for example A and C, so always there is only one unique path is available between them in the spanning tree. So more than one path is not possible in the tree. And next is in a tree, every pair. Oh, this is okay, done. Algorithms. Yeah, so there are two algorithms which we can use to find the minimum spanning tree for the graph. First is Prim's algorithm. Second is Kruskal algorithms. Okay, so first we will learn the Prim's algorithm. So Prim's algorithm is approx similar to digest algorithm. So we will see the concept. What is the similarities? So for example, this is a graph, and we will compute the minimum spanning tree for this graph is. Okay, so yeah. So in Prim's algorithm, same things. We will apply the algorithm similar to the digest algorithms. So first things, we will initialize that we can start from any vertex in the Prim's algorithms. Okay, so there is no condition to start from any particular vertex. So we can start from any vertex. So initially we will assign that all infinite. Okay, and we will also mark that which vertex is visited or not. Okay, so initially all are false. So we will represent that false, 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 and false. Okay, so now we can start from any vertex. So for example, if we are starting from this 0, so we will mark distance as 0 and mark this is a visited. Okay, now we will update the distance adjacent vertex distance from this source vertex which we are starting from. So 0 to 1 we can come in the 10, so we will update this by 10. Okay, same thing. So 0 to 3 we can come in 18. So this is the first thing. At the time when we are selecting, so we will for a spanning tree, we will also store this information, parent information. Okay, so for example 0, 1, 2, 3 and 4. So for 0 there is no parent, so we will store this none. After that we will select the vertices which contains the minimum distance. Okay, so what is the next selected vertices? This is already selected. Now next is 1. Okay, so we will mark that. So at the time of selection, so this 10 value, where from we get this information, where from get this distance 10 is 0. So at the time of selection we can mark this parent information 0 here. Okay, so after that we will update the distance for the next adjacent vertex, but we will not consider the previous visited vertices. So 0 have already visited, but will not update this information. So now we will mark that now 1 is, this become traverse true. Okay, now the changes only is this. So from, if we are considering that the distance from 1 to 2 and 1 to 3, so we will not add the previous distance here. In the digestion algorithm we always add the previous distance because we are calculating the distance from the source vertices, but here we are interested to find out the minimum spanning tree. So we are just interested to find out the minimum edge which are which will be included in the spanning tree. So we will not add this previous distance to find to update the distance of adjacent vertex. So 1 to 3 is 6 and the previous value is 18, so we will update this by 6. Okay, and 1 to 2 is 20 and previous is infinite, so 20. So this 6 is we are getting from 1, so 3 we will update this by 1, and 2 we will update this by also 1. Okay, same thing. Now our unvisited vertices are 2, 3 and 4. So what is the minimum distance is 6. So now we will check that from 3. So we can, so 0 and 1 have already visited, so we will check that 3 to 4 only. So 6 plus 70 is 76. Okay, so this will be updated 76. So we will update that. We will receive the information 4 to 3. Okay, only one node is updated. Now we will so this have already visited, true. Now only 2 nodes are remaining, unvisited nodes are remaining. So
why are we doing 76 here?
oh sorry, not 76, 70. Yeah, correct. Okay, so 70. Now we will check the next minimum distance with vertex is 2 and check that what is the adjacent which are not visited. This is 4. So 20, no, we will not add this 20, sorry. So this is 8 and previous is 70. So we will update this by 8. So and where we are coming from 2. So we will update this by 2. Okay, so we have completed this. Now from 4 node there is no node available which are not visited. So this process is completed. Now we can create a spanning tree using this parent information. Okay, so for we will start from this parent information. For example, so we will mark that, so 0, 1, 2, 3, 4, or we can directly, so 4 to 2. So 4 to 2, this is 1 as is considered, 3 to 1, 3 to 1 as is considered, and 2 to 1, 2 to 1 as is considered, and 1 to 0. So this is, so this is a so this is 10, and this is 1 to 2 is 20, and this is 6, and this is 8. So total, this is a spanning tree for this graph is, and total cost is 10, 30, 36, and 44. So this is the minimum cost for spanning tree. So this is the Prim's algorithm. Okay. So we can find out the minimum spanning tree using this Prim's algorithm concept. So this is similar to digest algorithm. If you have implemented the digest algorithm, so you can change some smaller things in the digest algorithm, and you can change to the Prim's algorithms. And the next algorithm is Pascal algorithm. So in the implementation of the Prim's algorithm, some part is actually extra part. So there is no work in the implementation. So if you try the implementation by yourself, so that will be better. So there is some extra part in this implemented code. So we are not using this extra part. Right. So we will update we will add the new updated code in this node side. Okay, so don't confuse by this extra part. And the Pascal algorithm, next is Pascal algorithm. So what is the concept of Pascal algorithm is? So for example, this is a new graph. So in Pascal algorithm, that is a simple algorithm. So we first find out the all edge information. What is the edge weights is. So for example, so if we are considering that these are all are the edge, so first we will arrange the edge in increasing order of their weights. So for example, if you mark the name for each edge in the graph, so for example, this is E1, this is E2, this is E3, E4, this is E5, this is E6, and E7, E8. Okay, so we will first we will arrange these edges in increasing order of the weights. So which one is the smallest weight is so 5 to 6. So we can see that 5 to 6 is 5, and next smaller is 6. So 1 to 2 is 6. Next is 10. So there are two, so we can mark any. So 0 to 1 is 10, and 4 to 5 is also 10. And then next is 1 to 4, or one more is 10. Okay, so 4 to 6 is also 10, and 1 to 4 is 20, and 0 to 2 18, and 2 to 3 is 70. Okay, so 1 2 3 4 5 6 7 1 2 3 4 5 6 7. Okay, so this is the first step of Pascal algorithm. After that, we will include these as in the same orders. First we will start from the minimum cost edge, and we will mark that this edge will be considered or not. So for example, if we are starting, if we are just marking that, so in the same I will mark by the different color. Okay. So first we will start from 5 to 6. So we will mark that if we are considering this 5 to 6 in our graph, so is there any cycle is created or not? So consider that there is no. Okay, I'm just creating a vertex separately, otherwise some confusion will be created. So 1 2 4 5 6 and 3. Okay, so first we will start from the source minimum cost as 5 to 6, and mark that this is in our spanning tree. And at the time of marking, we will check that is there any cycle created after considering this edge or not. So there is no cycle is created, so we will mark that in our final spanning tree. After that, 1 and 2, so if we mark the edge from 1 to 2, 6, so there is no cycle is created. So same things, 0 to 1, so there is no cycle is created, so this is 10. 4 to 5, so 4 to 5, if we included that, so no cycle is created. Now 4 to 6, if we are adding this 4 to 6, so one cycle is created. Okay, so we will not consider that 4 to 6. And 1 to 4, if we are adding 1 to 4, so this is 20, there is no cycle created. So 0 to 2, so 0 to 2, if we are adding that, so definitely cycle is creating, so we will not consider that. 2 to 3, so 2 to 3 we can also consider that, so this is 70. Okay, so this is the minimum spanning tree for this given graph. Is if you will create the minimum spanning tree using Kruskal algorithm or using Prim's algorithm, so same spanning tree will be created. Okay, so the result will be same, but the algorithm is different. So this is the basic concept of Kruskal algorithm. So in the implementation, so how you can check that if after considering the edge cycle is present or not. So we use some component information. So for example, we store some component value. So I'm just repeating all the part. This is the basic dry run. You can directly solve if in exam this one graph is given, then find out the minimum spanning tree cost. You can directly apply this algorithm. But in the implementation, how we can check the if cycle is coming or not after considering any edge. So we contain one information component. So after every edge, so for example, if we are starting from this 5 to 6, so at that time, so initially all vertex are different components. Okay, so and the initialization is the component of 0 is 0, 1 is 1, 4 is 4, 2 is 2, 5 is 5, and 3 is 3, 6 is 6. So according to the algorithm, so we are assigning one component information on each vertices. After that, we will check that at the time of edge considering, so we are just starting from this 5 6 edge, so we will check that the component of 5 and 6 is same or different. So the component value of the 5 is 5 and 6 is 6, both are different, so we will consider this edge and we will update the component. So for example, if we this 5 and 6 we have added, so we will update the component. So we will either update the component by this 6, or we can also update this 6 component is 5. So now after adding the edge between 5 to 6, the component will become same. Okay, now for example, we have marked that this is 6. At the second time, same thing, so 1 to 2. So for example, if we are marking the smaller value as a component, so now we are changing this 5, we will follow the same rule. So 1 to 2, 1 to 2, now the initially component is different, 1 and 2, so we can add the edge, and after adding the edge we will change the component of the smaller value, so on the both 1. Okay, so 0 to 1, 0 to 1, so value 0 is 0 and this is different. So here now after adding, so now the component of 0 1 and 2 will become 0, smaller values 0 0 and 0, because all three vertices are connected now, so all the component value will be same, the smaller vertices value. Okay, at the next time 4 to 5, so 4 to 5 if we are adding, so the initially the value of component is 4 and the component of 5 is 5, So after adding, we can add because the component value is different. So after adding, we will update all the components by the smaller value. So this is become my 4, and it is also become 4. Okay. Now next thing, 4 to 6. So 4 to 6, if you see that, so now the component value is similar. So 4 is 4 and 6 is also 4. So at that time, if you are receiving the components value is same, so that means that edge is considered as a cycle edge. So you will not consider this edge in a spanning tree. So at any time, if you are getting the 4 to 6, so for this is considered as a U and this is considered as a V, the component value of U and V are same. So definitely that edge is creating a cycle. So we will not including this. So same for the 1 and 4. So 1 and 4. So the component value for 1 is 0 and 4 is 4. So we can add this. But after adding this, we will update all the component. So now it becomes 0, it becomes 0, it becomes 0, all the 0. Now next is 0 to 2. So 0 to 2, now this contains 0, this is also contains 0. That means we cannot add this edge. And 2 to 3, so 2 is 0 and 3 is 3. So we can add this and then update this value 0. So this is the process to implementation of this traversal algorithm. So if you see the code, so same things, we are just assigning this component value for each vertex as initially u equal to u, and after we are sorting these as, then we are considering each as one by one and check that the component of u is equal to v or not. If not equal to, then we are adding up, we are considering this edge. If equal to, then we are not doing anything, we are ignoring this. Okay. So if component is different, so we are considering this edge in our spanning tree, and after considering this edge, we are updating all the components here, value of all the components which are connected. Okay. So this process we are using in the traversal algorithms, and we are getting this minimum spanning tree information from using this traversal algorithm. So these are the topics which we are running in the peak 5. So if you have any query, then you can ask, or if you have any query from mock, then you can also ask. So any query regarding from peak 5 and any other, any mock in mock? Hello, any query? If you have any
I think
query,
we can discuss in revision session.
okay. So on Friday, so come with the queries. So after solving the mock paper, so I think someone is posting the link of sites which have previous papers. So you can also see the question from the previous term papers, and then we will discuss in the revision session all these things. Okay.
If I mean, in revision session you can come up with some few more practice problems other than what have been discussed for calculating O and all things. So that is
Complexity,
going
no?
to help us. Complexity. I mean,
Okay,
omega,
okay.
theta, ego. So that is going to help, I think, for all of us.
Okay, okay, sure, sure. So we will discuss some complexity based problem. Yeah, okay.
Yeah, I mean, taking the different examples and then discussing the methods and the concepts.
Okay, okay,
That
sure.
will help. Yeah.
Sure, sure, sure. Okay. So I think there is no question. Okay, so we will see the all topics in the revision session on Friday. Thank you everyone.
Thank you. Good night.
Good night.